welcome to Conversations with. I'm Courtney.
And I'm Keith.
And we're the clinical team here at Burtons Academy. With our combined passion for monitoring and ventilation, we're here to rewind and remind you on the foundations and principles used to form the knowledge and understanding in everyday anaesthesia.
And today we're going to talk about carbon dioxide. And again, when I started thinking about carbon dioxide, I thought this is a smaller subject than oxygen because oxygen is the dominant thing. You breathe in oxygen, and it's all about oxygen. But actually, when you start to look at it, it's nearly all about carbon dioxide, and there's far more about carbon dioxide that we need to talk about than we do with oxygen. So I'm joined by Courtney. Hi, Courtney.
Good morning.
And we're just going to go through talking about carbon dioxide today, and possibly into the second part of this, which will be episode 5. And we're going to follow. Well, Courtney, where should we start with carbon dioxide? Where do you think is a good place to start?
Oh, I think, as always, perhaps starting from the very, very beginning, perhaps how we even form carbon dioxide and where it's formed and how we have to get it out from there. That to me seems like a really good place to start.
Okay, so we're going to start right down in the tissues then, wherever we are, whether they're in bone, whether they're in brain or muscle or wherever we are, gut.
Yeah,
liver.
back to the beginning.
Back to the beginning. So we've got all these cells producing carbon dioxide as a byproduct of metabolism. And I think we just need to refresh ourselves about that metabolism. So if we're burning pure sugar, C6H12O6, and we combine that or burn that, we produce carbon dioxide and water. Yeah, and I think we get lots of ATP from that, but we're producing CO2. Yeah, and it's a oxygen to CO2 ratio 1:1. So our R ratio or our value is 1. Yeah, so if we look at respiratory quotient, it's 1. Do you remember respiratory quotient? So if we're burning pure sugars, we've got respiratory quotient of 1. But we start burning fats, they don't produce oxygen in the same ratio consume oxygen, produce CO2 in the same ratio. It's more like 0.7. So depending on what the body's doing, how much glucose it's burning, how much fat it's burning, you get this variation between 0.7 and 1, the respiratory quotient.
So that means whenever I've looked and I've got lost down some of my textbooks and I'm looking at these calculations that come up in regards to respiration, I always see the respiratory quotient as 0.8. And is that why?
Yeah, it's an average.
Okay. I like that. Okay.
Yeah,
it makes a lot more sense to me.
That's right. So on average, we would, burn mostly carbohydrate, but some fat. And so our respiratory quotient tends towards 1, but it's not quite there because it's not pure carbohydrate that we're burning.
You need to write that in the book, Keith. We need to put white out in all of these books and have you just write that sentence and say, this is why it's 0.8. Because I have to think, why is it 0.8?
Why is it 0.8? Yeah, exactly. And, and a lot of our calculations like the alveolar gas equation assumes that it's 0.8, but it may not be. So when you work out a very precise alveolar PaO2, big A oxygen level in the alveolar, you're assuming, because you don't know what the respiratory quotient is, you're assuming 0.8. So you do CO2 over 0.8 or whatever the CO2 is over 0.8 to give you the effective value for oxygen. But it could be 0.7, it could be 0.9, depending on...
Based on all the different ways there's metabolism happening.
Yeah.
That was
So it varies, yeah.
I thought it might be a moment. Thank you. Sorry about that.
That's right.
Skip down the calculation path very quickly this morning. Okay.
So there we are. We're producing all this carbon dioxide, and the body's got a problem then, really, hasn't it? It's producing a lot of carbon dioxide, and carbon dioxide is very soluble, as we mentioned before. So it's going to fill up all the surrounding aqueous tissue, when obviously the whole body is bathed in tissue fluid. So we've now got a body which is a fluid vessel, really, with just a sack of skin holding a fluid container of ourselves, supported by bone, in terms of things diffusing. So now it's just full of CO2, and we've got to get that out, because if we don't remove that CO2, we'll just create a very acidic tissue fluid, and then things will go wrong. So I'm making something that happens all the time that we all understand. Sound very complicated, but basically capillary flow through the tissues is going to pick up that CO2, take it to the lungs and get rid of it. And that's, I think, where we all start in school about learning about that. And I think as we were just saying before the podcast, it's a very nice, simple story. And when you start to look into it, it gets more and more complicated. And it's amazing how neat this is. I get very excited about how neat this whole system is. The red blood cell is a I think probably not misunderstood, but just not recognized for what it does. I mean, I used to think red blood cell picks up oxygen and delivers it, but you don't really think how it does it. And it's just amazing. So we'll start looking at this amazing feat of natural engineering to get that CO2. First of all, get it into the red blood cell. And what happens then? So this CO2, we know it diffuses rapidly, so it'll easily diffuse from the tissues into the capillary, into the plasma, and then that plasma is packed full of red blood cells. So immediately it's going to that CO2 is going to pass into the red blood cell. Okay, and then three things happen. One is the CO2 dissolves in the fluid within the red blood cell partially, and we get about 7 to 10% there. So small amount there. And then CO2 combines with water to form carbonic acid. That's CO2 plus H2O because H2 is CO3. Now, if you do that in a glass of water, you add some CO2 to some water, like your soda stream, it'll take about 1 to 5 seconds for that CO2 to go through that process of CO2 plus water forming carbonic acid and then dissociating to H plus and HCO3. The H plus and HCO3 is rapid. So it's the bit going from CO2 and water that actually change into carbonic acid that takes quite a time. So we can't wait 5 seconds in the lung, in the tissues. So what's really neat is as soon as the CO2 gets into that red blood cell, it finds itself in an environment where it's got a lot of carbonic anhydrase. And there are lots of different types of carbonic anhydrase. It's an enzyme, and it speeds up that formation of carbonic acid. But it's phenomenal how fast it does it, Courtney. So it does it 5,000 times quicker than it does if it wasn't present. So let's say it would normally take 5 seconds. So now it's taking 1 millisecond. Once you're in a blood cell, it can do that conversion in 1 millisecond. I mean, that is just amazing. And what in an anthropomorphic way, what the red blood cell is doing is going, okay, I'm in this situation. I'm going to use carbonic anhydrase to find out how much CO2 is in this solution. Now, it uses that as a tool because that converts all the CO2 that's come into it into carbonic acid, and hence then into protons and HCO3 in a fraction of a second. In that 1 millisecond, it goes. So it instantly knows from the moment it arrives in that tissue by the use of carbonic anhydrase how much CO2 is in that tissue. That's its little test. It uses that to find out. So now it's produced amazing amounts of protons and HCO3 minus in a fraction of a second. Now the protons then go and bind with the hemoglobin, okay? And that changes the structure of the hemoglobin. And what happens is then, because it changes the structure, it releases its oxygen. That action of that binding changes the oxygen. So the oxygen is then released. Okay, so the oxygen now is going to go off and diffuse down its diffusion gradient into the tissue. And because it's lost its oxygen, it now becomes receptive. So it's gone from its R state to its T state. It's now receptive to CO2. So the CO2 that was in the fluid in the red blood cell is now going to bind very, very quickly to that hemoglobin. And it's going to carry about 25% of the CO2, that hemoglobin. And having done that, it's produced that carbonic anhydrase reaction has produced lots of bicarbonate. So much so that it's now diffusing out of the cell back into the plasma in exchange for chloride to maintain this neutrality. And this happens in such a tiny space of time, milliseconds. So this is evolution at its best. You've got this CO2 that was not very soluble in water. It's not very quick to form carbonic acid. This carbonic anhydrase in the red blood cell just like that, zoom, immediately tells the red blood cell, tells the red blood cell how much CO2 is there, converts it into protons and bicarbonate. Bicarbonate shoots out the cell because there's lots of it, goes into the plasma. And that's why there's 70% in plasma. Protons stay in and are buffered by the hemoglobin so the pH doesn't change. and that change in that buffering state changes the conformation of the red blood cell, and now it binds with CO2, and it loses its oxygen, all in a fraction of a second. So I just think it's such a neat thing, Then it passes out of the capillary. Once you're out of the capillary, you've got non-permeable membranes, and it stays in that state. We're back on the tube again now. We've got on the tube, and we're going down that tube line, and we can't get off until we get to our destination station. And then when we get to our destination station, doors are going to open. The environment's going to be different. We'll come to this later, but then it's going to be a different story again, and all the effects on whether you lose oxygen or not, the Bohr effect, all those things are then going to affect the other end. But down at this end, we've got that really neat behavior of red blood cells to lose their oxygen and pick up CO2. And it's that process that it first loses its oxygen because the concentration gradient that sets off the chain of events that the CO2 is then able to bind with the hemoglobin, and the carbonic anhydrase makes it happen so fast. And the whole thing is, I think, amazing.
I think it's incredible, and as a visual learner, I've looked at so many Google images of this happening, and then having you just verbalize it like that actually really helps solidify it. So if people listening are also visual learners, I just type into Google often like carbonic anhydrase red blood cells, and there's this nice picture of a red blood cell and a cellular membrane, and then it just shows all of those
three classic pathways.
Yeah, all just moving on a picture. And then I think have a look at that online. Just Google that. I just use those keywords like carbonic anhydrase red blood cell, and then listen again with how Keith is describing it, like how you just described it there. I've been looking at these pictures for a long time and trying to go, okay, and that must go there, and then that goes, but what is that doing over there? But I think just now I was able to merge the two of them together in my mind and listening to you, and that sounds perfect. It does sound really complicated.
It is complicated.
And this is why I laugh, because it was only last year we just done a big congress, and I was really tired, and we're on the train in Switzerland. I think I was semi falling into a slumber on the train as we were both heading to the airport, and that's when he turned to me and he said, I don't know about all of this, science stuff. How can these red blood cells and everything just work so perfectly? How can it happen all so quickly? I thought, oh no, I'm not napping anymore. It's so fascinating.
It is an amazing feat of, I say, natural engineering to do that. So the red blood cell plays a huge part in carbon dioxide transport, and you could, when you go through school and even perhaps university or training, you don't relate the red blood cell with CO2 carriage, do you?
I definitely just thought oxygen in, jumps on the red blood cell, gets a ride to the tissue, jumps off. And then I don't know what I thought the hemoglobin was doing after that, or the red blood cell was doing after that.
Well, no, exactly. And I suppose the other thing is we alluded to this last week, the last podcast, where hemoglobin picks up oxygen in the lungs, it's 100% saturated or 97% saturated, and it drops it off in the tissue. And I just thought it dropped off in the tissue, that's it. But of course, it's still 75% saturated. It doesn't lose it all. There's a huge reserve there, and that reserve is there for things like exercise, where you've got a lot of CO2 production and you're producing effectively an acidic environment, and that changes because that Bohr shift changes that releasing power of oxygen. So instead of coming back with 75% saturation, it comes back with 40% saturation because it's lost a lot more oxygen. I mean, it didn't really occur to me that these things were going on. So it's a fascinating story. But as I said at the beginning, carbon dioxide forms a much bigger picture than oxygen. Oxygen really comes in as the fuel for the rest of what goes on. Now we've got carbon dioxide, and okay, so we got it into the red blood cell. We know it's in there, and it's in the blood, and the bicarbonate has, formed that buffer, 70% or so in the plasma now. But that blood is everywhere, and that blood is going to have an enormous effect, containing that CO2. The CO2 effects on the body are, I've listed them prior to this podcast, and there's just reams of the effects of carbon dioxide, whereas the effects of oxygen are easily summed up. Really, it's fairly inactive. It doesn't do much apart from being carried to and then provide oxygenation for cellular metabolism. But now we've got carbon dioxide. And we know how it gets into the red blood cells. So we now know it's bound to hemoglobin. Some of it's dissolved as CO2, because that's really small, 7%, 10%, 25% or so, 30% is bound to hemoglobin, and the rest is buffered by bicarbonate. So it's got a big influence now, what CO2 can do. And we can maybe start to look at what the effects of CO2 are. Yeah. One thing just to go back to on the red blood cells, I talked about the carbonic anhydrase. What's interesting is there are 16 different enzymes, isoenzymes of carbonic anhydrase. And so the astute people would have said, okay, if you need carbonic anhydrase to convert CO2 to carbonic acid, and it's a reversible reaction following that Le Chatelier's principle, you're going to need carbonic anhydrase to go back the other way. But it can't be the same, because you can't have one enzyme doing one way and one doing the other. And they're absolutely right. So you've got type 2, I think it is, doing it in the red blood cell. When we get back to the pulmonary capillaries, we'll talk about it later. When you get back to those capillaries, you've got carbonic anhydrase type 4, and it just does it the other way. So when you get to those tissues, the whole thing gets reversed just by the presence of a different form of carbonic anhydrase, forcing it the other way in the lungs. So really, really clever. There are obviously 14 other types of carbonic anhydrase spread around the body. We won't go into those, but it's just fascinating how something can speed up a reaction so quickly and make that whole mechanism work. Okay, I probably waxed enough about how red blood cells exchange oxygen and CO2. Let's think about what all that CO2 is going to do. It's kind of a lot of effects, isn't it? We talk about a lot of our ventilation talks and our capnography. We talk about the constant rate of production of CO2, and I think that's an important thing to talk. Yeah, because it is constant relatively, particularly in anaesthetized patients lying on a table.
Mm-hmm.
So we've got this constant rate, but there are going to be some medical conditions or environmental conditions which are going to change that rate of production. So we can't always assume it's constant. Most of the time it is, but we need to be aware of when it might not be. And I think there are 4 classical effects. So hypothermia, hyperthermia, hypothyroidism, and hyperthyroidism. And I know, Courtney, leading up to this, we've had quite a few discussions about the relative merits and influences, and we've done a lot of searching for papers to support this. So I think you've got a good summary of the effects of those 4 different things: hypo and hyperthyroidism, hypo and hypothermia. Maybe we'll start with the temperature effects, and then we'll look at the thyroid effects. Do you want to let us know about what you found?
Yeah, well, it's one of those things where the more you look, the more you realize it doesn't exist or you can't find it. But I always think if we're constantly producing CO2, just like you said, although we're constantly producing CO2, the rate at which we produce it isn't just a static constant number, and we've got lots of different things that can affect it. And I always think back, if it is to do with, if it's produced as a byproduct of metabolism, and if we have perhaps an environment that causes us to produce more because our metabolism has changed or less, then I think, are we actually producing more or less CO2? Or by definition, has our metabolism, I just get down these wormholes, has our metabolism decreased and therefore we should be producing less? And if the metabolism's increased, should we be producing more? So I think we can talk about what, on paper, you would think this. So for example, if we have a patient that is cold and they're hypothermic, then their metabolism has slowed down. So although they're still constantly producing CO2, the rate that they were producing it under anesthesia, well, even before they were conscious, it's not that rate that they were doing it. They're perhaps producing a little bit lower. So I actually have seen, or feel like I have seen, a patient that is quite hypothermic. And I'm talking for some of the length of procedures and procedures we were doing where I used to work, it wasn't uncommon. I'm not saying this is okay. It wasn't uncommon that some of those patient temperatures were, 30 degrees, 34 degrees. And I always did feel like their CO2, their end tidal CO2 was actually lower because of that. But now, was it lower because they were so cold and they weren't able to get the breaths out, and therefore what I was able to read in that moment, I don't know, because I just got down these wormholes, which conversely, if you flip it over, we're more likely to anesthetize a patient and have them become hypothermic than hyperthermic. But if we had a hyperthermic patient and they had a really fast metabolism because of that, potentially are we going to see an increase in CO2 production? By definition, you kind of would assume that you would.
Yeah.
But there's so many other factors.
And I think you do. I think these heat stroke dogs that, running temperatures up to, 39, well, I'm in old school, so up to 100, 405 degrees centigrade.
Yeah.
Hot dogs, they are pumping out a lot of CO2. That's well documented. So I think definitely they are. And the dogs that fall through ice into ponds and things, okay, we don't see those every day, do we? But they, again, definitely are really low on their reduction of CO2 down. So but that's extreme. So what the effects of 2 or 3 degrees drop and 2 or 3 degrees rise are, I don't know, but the extremes definitely. So we definitely got that effect going on. Yeah.
And that's when we had those really, really cold cases. It's usually those tiny cats, unfortunately, isn't it? It's a cat having a neck slap, or I remember one time I had a patient that was having oh gosh, did it lose it lost its foot or something like that. It had a massive degloving injury and it was having a skin graft, and the graft was being taken from its whole side of its body, which meant a massively shaved and prepped cat. And this cat was the coldest cat of my career. It was literally 30 degrees. And I had a horrible time. But the CO2 production of that cat, it was so low. There was, my CO2, my capnography there was a number there, but it wasn't being ventilated with this cat either. It was just a really low number. So I find those much more easy to wrap my head around. If you have if you're hypothermic and you are producing more CO2 because your metabolism's higher, that makes sense to me. The hypothermic patient has a really low temperature, a low metabolism, therefore surely they must be producing less CO2. But it's the wormhole of endocrinopathies that I skip down and start questioning a lot.
Maybe before we just go to that, what about malignant hypothermia? That's something that's seen, and I think greyhounds and what's the other breed?
Pigs. Well, I know pigs get malignant hypothermia.
Pigs get it, yeah. So it is possible that you clinically could see a case of malignant hypothermia, and it would definitely have a increased CO2. That would be a clinical manifestation of it. So I think it is possible for us to see these cases clinically. Yeah.
And I think, is it malignant hypothermia also causes a hyperkalemia, doesn't it? And that must all be related to
the CO2
carbon dioxide. Yeah.
And, well, I guess to what is basically a respiratory acidosis. Yeah.
Yes.
Yeah, or an acidosis. In a general sense. Yeah, but respiratory based acidosis. So that's going to lead to a hyperkalemia. Yeah.
Hyperkalemia.
Yeah. So that's one of the things I was going to talk about later. We can, as we move straight on to that. Yeah. This effect of CO2 is widespread. Really is. So increased levels of CO2 do lead to respiratory acidosis, and those pH changes have an effect on potassium going in and out of cells, because potassium in and out of cells is governed somewhat by insulin, isn't it? By the passage of sugars into cells and other solutes into cells. So if you get high CO2, you can end up having more potassium, more extracellular potassium than you would normally have, and so you start to see an increased potassium levels. So you get a hyperkalemia, and result, initial effect on the heart of bradycardia, and then effects on the T wave and the spiking of the T wave, and then eventually to arrhythmias. So it's a massive potential effect CO2 we can have just by changing that. So sorry, yeah. So I've gone off on a little bit of a tangent there.
Oh no, I'm nodding, going, I have had those cases before where they have had a respiratory acidosis, or I've looked at their CO2 and gone, what? And taken a blood gas sample and then seen the potassium really high as well and gone, oh dear.
Yeah, yeah. So again, the effect of CO2 is quite profound. So coming back to you were just going to talk about thyroid now and
Oh yeah.
hypo. I think we can probably relate, can't we? Hyperthyroidism would tend to suggest a higher metabolism, so that would tend to suggest similar effects from hypothermia. Is that right?
Yeah. I think when I've done a bit of a textbook dive on this and done a bit of a literature search, and when we do have hyperthyroidism, we have, that metabolism has increased. But I couldn't really find anything that quantified that the level of CO2 that is also increased.
Mm-hmm.
I couldn't find, it says in these books, as clear as day, doesn't it? I had books all open over the laptop last night and we were having this chat. And it says right then and there, it says, you will get an increase in metabolism. But how do we quantify that? How do we actually measure that is truly occurring? Are we seeing more CO2? So if I was to just simply look at it and say, okay, a hyperthyroid cat will have a higher metabolism and therefore might produce higher levels of CO2. And then conversely, that hypothyroid dog, that big Labrador, if it's got hypothyroidism, it has a decrease in metabolism. Our textbooks will say that. But once again, when I started to search into it, I couldn't really find anything published in veterinary medicine. But I did start to see some stuff in human medicine that said, of course, yes, they do have this hypothyroidism and lower metabolism, but actually they end up having normal-ish CO2. So this was when I was trying to distinct, well, surely black and white, but it was really not very clear because some of these disease processes, they cause a change in ventilatory drive. They change, if you think about your hypothyroid dog, when we anesthetize them, one of our really big concerns that we have with them is neuropathies, where they maybe get a laryngeal paralysis or they have this big belly that's pushing up on their chest, and that's reducing functional residual capacity, or maybe they've got respiratory muscle weakness and can't get their CO2 out. So actually, in those cases, I can't find anything, but I would love it if someone did have something incented on. I can't find anything specifically that says, oh yes, your hyper or hypothyroid patient will have a decreased production that's measurable of CO2. I couldn't find that.
No. But I think that there's maybe other things going on there as well, because your hyperthyroid case, yes, initially, if you could induce hyperthyroidism, so 9 o'clock they were normal, and at 10 o'clock you made them hyperthyroid, then you get a response. I can see that. You get a metabolic response, you get an increased CO2 response. But that increased CO2 response is going to be buffered by all the systems in the body. The bicarbonate system, you're going to get a shift in bicarbonate. We're going to redress the pH. We're going to change the ventilation, and everything's going to come back to normal to cope with that hypothyroid condition. It's going to take days, but it will come more settled towards normal. If you then give another step change in thyroid, you get the same slow response, but you'll get a response. So when we see a hypothyroid animal, it's chronic, isn't it? So had all those adaptive changes have gone on. So I think there's all the mechanisms responding there, so that when you're right. Theoretically, a hyperthyroid animal must be producing more CO2, but I think you get normal adaptive changes, so that by the time you see it, you don't see a hypercapnic animal.
Yeah.
You have a normocapnic animal, but I guess if you were to look at underlying acid levels, acid base levels, you'd see distortion there because of the adaptive effect. You actually may see changes in bicarbonate levels, so it's slightly higher, which is a long-term response to the potential hypercapnia. So,
and that makes so much sense, like the acute or chronic, because that happens with lots of other different disease processes as well, isn't it? If you have a massive blood loss or some kind of sudden anemia where maybe you've given a lot of paracetamol to a dog, perhaps, and suddenly their haemoglobins aren't functioning as they used to. They can't cope with that reduction in oxygen or the lack of oxygen carrying capacity. They can't cope with that. Whereas you get these medicine patients that come in with PCVs of 8 and they're wandering around, they're just wandering around. You think, well, how are you doing this? And because they've had so much time to adapt. And it must be the same thing for these patients with these endocrinopathies. It's not acute.
No. So I think, those 4 factors we talked about, constant rate of production. So there are things that affect the rate of production. In the operating room, we're really going to be concerned with hypo and hypothermia. I think there's going to be temperature effects, and there's possible cases of malignant hypothermia affect that. Okay, so maybe one thing we could just talk about. It's a purely physiological principle, and I don't know, the people listening, some may be listening for practical insights and little clinical gems. Some perhaps are listening for deeper explanation of physiology and what have you. One of the things I really enjoy, as you know, is the deep physiology. We need to talk about, I think, the Bohr effect and the Haldane effect, just because it comes up in textbooks. It comes up in exams for diplomas on doing the anesthesia exams. But it's quite interesting, and it's very clever. It's just another modification of this red blood cell carriage of CO2 and oxygen, which is quite intricate. Is it something that you covered at all in your nursing training, Bohr effect?
No.
I think it's a bit deep, really, isn't it? Yeah.
I mean, we say it's a bit deep. I know the first time I ever heard those words ever in my life was probably maybe January or February last year, when you and I were in a room drawing the dissociation curve on the wall, and you said to me, "Oh, you know about that one, don't you?" And I thought, I've never heard that word in my life. But now that I do know it, the Bohr and Haldane terms and the effects, and actually that they're named after real people. Why isn't this taught? Why is this not? How could this not be taught?
No.
How can it not be taught is more probably my feeling towards it now. So
yeah, I mean, absolute pioneers of this stuff. Christian Bohr, 1904, he released his paper on the Bohr effect, which he worked. I think he started working with his colleagues in 1903, but in 1904, he released this a paper on the Bohr effect, which basically says the Bohr effect is that the oxygen binding of hemoglobin is influenced by 4 main factors: pH, hydrogen ion concentration, CO2 concentration, 2,3-DPG, which is a constituent of red blood cells, 5, and temperature. Yeah, and all of those cause a shift in that dissociation curve. And this is, I think we crossed this before. This is a slight beef with me about the oxygen dissociation curve because it's slightly misleading. What is better to think of is a dissociation curve, the normal one, and then in the lungs, and you're right up at the top right hand side of that curve. You're picking up oxygen. Now shift that whole curve along to the right a bit. Now you're talking about the situation in tissues when it arrives, and now place yourself down in the bottom left corner of that curve, because that's where we are for oxygen in the tissues, and that difference between those two oxygen levels, saturation levels, is the offloading of oxygen. So Bohr described the binding of oxygen related to different tissue conditions, and he did it initially with pH, but it is affected by those 4 other factors as well. So that's the Bohr effect. And the Haldane effect is describing the opposite in a sense. It's looking at how the oxygen levels affect binding of CO2. Okay, so when you've got low levels of oxygen, you've got better binding of CO2. When you've got high levels of oxygen, like back in the lungs, you've got poor binding of CO2. And it's not a linear thing. It's the Haldane effect, because of that conformational change in that hemoglobin structure. it doubles the ability for hemoglobin to carry CO2. That is the Haldane effect, because the more oxygen you have, the more difficult it is to bind CO2. The less oxygen you have, the easier it is to bind CO2. And that is a factor that controls it, rather than just being a one-to-one relationship. So that Haldane effect increases the ability to carry CO2 or to lose CO2. So that's the Haldane effect. So the two are related, but one Haldane effect relates to the way CO2 is carried and the effects of oxygenation on that, and the Bohr effect relates to the carriage of oxygen based on its environmental conditions. So does that kind of clear things up a little bit?
I mean, it does for me, because I've been staring at my post-it note that has a very erratic looking drawing of the dissociation curve, and hearing you say that once again against my visual picture of the graph, it does. I'm just like, oh, of course, that makes a lot of sense. We need that change in the tissue so that the oxygen hops off, the CO2 gets on and it gets out of the tissue where it's been produced and comes back, and then we need that change again in the lungs.
Yes, and these two effects, really what they're doing is kind of adding an explanation to what I said earlier about this mechanism for oxygen loading and CO2 offloading down in the tissues. And obviously they described it, and you have to commend them back in 1904. And
was Haldane centuries before? Was Haldane quite a time ago?
He was before. Yeah. So he was in the Haldane effect, I think, was described in the 1890s. They were the same era, but Haldane was kind of before Christian Bohr in describing his Haldane effect, if I remember correctly.
I wonder if they ever met, if they ever got into a scientific fight about it.
I'm sure they did. But you think, Courtney, to do that in 1904, so you haven't got capnography then, you're really working with very, very few tools compared to what we got today. We do a blood gas, it's there in a few minutes, isn't it? They had to work very, very hard to measure all those pH levels and CO2 levels. Incredible amount of work. Anyway, we digress. So there's a little bit about the Bohr effect and Haldane effect. If people hear about it, it's just they control the offloading of CO2 and offloading of oxygen. So we've got all the CO2. We've got CO2 in the blood, but it has, I keep saying, it has a lot of effects. So let's think about what effect it has on the brain. The number of effects it has on the brain. And we were going to pass through lots of tissues. It's going to have a lot of effects everywhere. But the brain. So normal mechanisms of CO2. We talk about respiratory center control. The breathing system, control of inspiration, expiration, rate and depth of breathing. That's all CO2 controlled. It's controlled by other things as well, I accept that, but it's also largely controlled by CO2. So when we start to run or walk fast or engage in any exercise, our CO2 production goes up. There's our change in metabolism. And if we didn't change our ventilation rate, then we would obviously build up more and more CO2. So automatically we get increase in ventilation rate, and that's done by that CO2 effect on the respiratory control centers in the medulla, which again is really clever because it's sensitive to CO2, not pH. It's absolutely sensitive to CO2 because the CO2 will diffuse across that blood-brain barrier into the CSF, whereas protons cannot pass across that barrier. So CO2 goes across nicely. So it's actually measuring the CO2. Once the CO2's in the CSF, yes, you get that dissociation to bicarbonate and protons, and then the protons are the ones that stimulate the medullary center and tell it how much CO2 is there. But protons themselves can't pass across, so it uses protons as a sensor, but only as a result of how much CO2 is there. So really clever to be able to respond to a proton signal that only comes from CO2. So it makes it very, very responsive to CO2. So in other words, it's quick. We start running, we start breathing faster to keep our CO2 removal constant and keep our PA, our arterial CO2 normal around 40. So so the CO2 is there to have an effect on the brain. But we have other effects. Well, obviously we've got the aortic and carotid bodies. It's going to be sensed by those two. and they're going to drive ventilation as well because they are sensitive to CO2. They're also sensitive to protons as well, but they are sensitive to CO2. And these little fun facts, about 70% of the respiratory control comes from those aortic and carotid bodies compared with the central control. I don't know why. You'd think it'd be the other way around, wouldn't you?
I would have thought it would be the other way around.
And I kind of had it in my head that it was the other way around, but maybe the minor moderation and control is finely tuned through the medulla, and the coarse control is done through the aortic carotid bodies. But about 80% of them control rate and depth of ventilation. So that CO2 passing through the body is having a lot of effects. So we've got CO2 as a regulator of respiration, and that's one effect in the brain. And then we've got the secondary effects in the brain, things like perfusion. And I think it's well known and been talked about a lot and practiced a lot that head cases where you've got the potential for increased intracranial pressure can be improved by reducing the intracranial pressure by reducing the cerebral blood flow. Reduce that cerebral blood flow, you can effectively shrink the brain. I remember going to, in my early career, going to a research facility where they were doing some live testing on I think they were monkeys, and they had the brain exposed. And during the whole of the procedure, they kept the end total CO2 at 20 millimeters of mercury. And towards the end of the procedure, they allowed that to creep up. And you could actually see that brain move and increase its volume within the skull. I'd never been so struck by how much something would alter something else. That CO2 definitely controlled that level of brain size, and it's a perfusion effect. So again, CO2 is having a massive effect on that. So there's another effect of CO2. I can't remember, Courtney, did you have something to say about cerebral perfusion?
Oh, I mean, having worked a lot doing MRIs and finding patients that had intracranial pathology and they had these space-occupying lesions, basically tumors, or maybe they were swelling, we would have to change the way we did breathe for these patients to try and manage the pressure within their cranium. So, and I think it depends on what you read, really, but one of the latest and greatest things that we have about kind of like head trauma anesthesia, or which you can adapt head trauma anesthesia to some other things like these space occupying lesions. So basically, if we have our bony, rigid cranium and it's not a flexible bit of bone, it's fixed in its size, we've really only got kind of three really important things in there, right? Like we've got the brain tissue itself, we have the CSF in there, and we have blood in there. So if there's an increase in one, something's got to change because that cranium can't expand to accommodate it. And usually it's going to be edema. Perhaps the patient's got some kind of trauma, they've been hit by a car, or perhaps there's changes in the tissue itself because there's this big tumor growing in there. So sometimes when you read text, and it's usually in old text, and I'm not talking about really old text, it could be kind of early 2000s, it says, right, if we can manipulate one thing to try and keep the intracranial pressure normal, we can't go and take the brain tissue out. We can't go and drain the CSF. In fact, the CSF's probably already displaced itself anyway. So therefore, we must be able to manipulate the blood flow into the brain. And we thought, okay, we can do that by hyperventilating these patients. If we bring down that CO2, we will cause a vasoconstriction. So if we have less blood in there, that's fantastic. So I feel like we used to aggressively hyperventilate these patients and bring their CO2 right down, maybe to the late 20s or early 30s. But actually more recent information says, whilst we're doing that, what we're doing is actually reducing the amount of oxygen also going into the brain. So if we're causing such a profound vasoconstriction, of course, we're reducing blood flow and therefore pressure. But what about this really oxygen-hungry organ that needs oxygen? Are we vasoconstricting too much? So actually, how we apply this now practically is we just think, okay, if we have a patient where we suspect we need to manage that blood flow into the brain because there's trauma, because there's some kind of pathology, there's got to be some kind of increase in pressure. actually just keeping the CO2 normal is more beneficial for that patient. Not so constricted that we're reducing oxygen, but don't leave them to dilate, basically. Don't leave that hypercapnia, because we will get a vasodilation. So whilst we don't want to constrict them, we just want to bring the tone back to normal. And actually, I was also just recently reading that these abnormal brains where they have had some kind of brain injury, or the way the brain works, it changes following that injury anyway. So they might actually be less reactive to levels of CO2. So all of your efforts will be in vain to try and vasoconstrict them. So yeah, now we just need to keep the CO2 nice and normal in those head trauma patients, and don't let it go high. Unless we are, of course, having a huge, big increase in intracranial pressure that's really sudden, and we need to very quickly try and reduce the pressure in the cranium whilst we grab mannitol, hypertonic saline, etc.
Yeah, I did also read some papers that suggested that the anesthetic agent concentration also has an effect on the response to the hypercapnia effects in the brain. So they tend to increase them. So yeah, if you have a lot of agent on board, then the brain is more sensitive to changes in CO2 than if there's not. So there's some argument there to try and keep your agent level low as well, because it moderates the effect of the hypo or hypercapnia effect on vasoconstriction. And the other thing I read is that hypocapnic vasoconstriction is probably more short-lived than we thought. So you might get the response for hours, but it's certainly doesn't extend into days. So again, I guess it's like all these things, it's an adaptive mechanism. You have the high CO2, you get the transient response, but then you get, and it's fairly, I think we talked about this as well, this is a fairly local response. You almost get a bicarbonate shift within the brain, so that you've got a response to that hypocapnia, as though you don't see that change so dramatically, or to the hypocapnia you get a chloroid response. So it may not be as long-lived as we thought.
Which makes sense, doesn't it? If everything changes, that has to also change eventually over time.
Yeah, and
the body goes, "What have you done?" Yeah,
it's trying very hard to keep all CO2 levels and things normal, so it's going to respond, isn't it? Have some other effect, yeah.
Because we want that effect just in the brain, but actually it's going to happen globally.
Yes, that's right. Yeah.
Poor body's going, "Why are you doing this to me? All this hard work." And it's like, I'm just going to put us back to how we were.
Yeah, and quite rightly, yeah. So I think that, so I was looking at the effects of CO2. So we're looking at the brain. We've got an idea of what happens there. But again, I say there are so many effects carbon dioxide has on, like, things like the autonomic effect. So I think we all appreciate that hypercapnia is effectively a sympathomimetic. We're going to stimulate what effectively is noradrenaline release by high levels of CO2. So we're going to see that as a result on our heart rates. We're going to see that on effects of vasoconstriction or vasodilation, depending on where we're going, hyper or hypo. And it's going to have an effect as well on things like cardiac muscle. So hypercapnia actually depresses cardiac myocytes, and it also has an effect on vascular smooth muscle as well. So it has an effect on that. But initially, when you get hypercapnia, you got that opposed by that increased catecholamine, the increased adrenaline response. So you actually see a mild increase in cardiac output and blood pressure when you get a hypercapnia. But all these effects are going on. I just think it's outstanding or astounding how much effect that little byproduct from wanting to get some energy from molecules of glucose leads to this byproduct, which then really is controlling many, many, many areas of the body, so many of them, and it has to be right. So our CO2 can't wander, because if it wanders, our pH wanders, and if that wanders, then cardiac myocytes get upset, brain gets upset, respiratory centers get upset, smooth muscle gets upset. It's just, isn't it phenomenal how much that is affected by one molecule? So I think, Courtney, what we can say is that CO2 production as a byproduct of cellular metabolism has enormous influences throughout the body. Something we haven't even talked about at all today is the pH of the blood and the effect of CO2 on the pH, and then the effect of pH on all these enzyme systems. And then, one of my favorite subjects, as you know, topics, Henderson-Hasselbalch equation, and again, I won't go into it here, but that is such a clever control of blood pH by something that's very, very finely controlled. That CO2 level very, very finely controls what the blood pH is, so cleverly buffered by bicarbonate. And the nice thing about the bicarbonate side of that equation is that bicarbonate is like a big, stable, think of it like a oil tanker out at sea. When you want to change direction, you have to make a decision 20 minutes beforehand. It's because it's so slow moving but immovable. That's bicarbonate in the body. It will change, but it'll change really, really slowly. So you have this rapidly responding variable CO2 that very, very finely tunes the pH, and you've got the bicarbonate, which is its reference point. But if you push that reference point long enough and hard enough, it will move and the whole body will get back to where it was. So if your CO2 goes up, you get a fall in pH, but your bicarbonate will go up over time and your pH will come back to normal as that response. That involves the kidneys, as I'm sure you know, as a slow response. But it just maintains that ratio of bicarbonate to CO2 at that 20, keeping that pH at 7.4. So again, we haven't got time to go into this. I think we're heading towards a podcast, aren't we, to talk about CO2, pH, and blood gas, because that's a phenomenal subject, and again, really, really clever how the body controls all those things. And it's interesting to look at all the knock-on effects of changes in CO2 and changes in bicarbonate. But we started off talking about physiology and relating to anesthesia, and when you start talking about pH and blood gas and acid base, you've got to start bringing in the kidney system because it has a profound influence. I have to be honest, kidneys always scared me because I never got my head around all those loops of Henle and the proximal convoluted and the distal convoluted. And it seemed to me that you started off with bicarbonate at the top and it pumped it out and then it pumped it back in again. Then it changed it for something else. Then it swapped it for chloride. Then it pumped it out again. And I thought, well, what's the point? Why not just bypass all this? And I wouldn't say it was taught badly. I was a bad recipient. I just couldn't really grasp it. And I still haven't fully. So it's probably a good exercise for me to go and look at kidney function. Fortunately, I just assume that the kidney does its job, and if we got a lot of CO2 and we need more bicarbonate, it'll change sodium excretion to retain water or let more water go, and all those effects. I just assume it does it. It's a little black box to me, and if you feed in extra CO2, it'll feed out extra bicarbonate to compensate. But it's a bit more complicated than that, obviously. But I think it would be worth us doing a podcast, because I'm certainly au fait with the pH side of things and how CO2 affects that, and that really, really clever mechanism, which I need to go into more detail to explain why it's so clever and so effective. But what I'm hoping this podcast has done, because we need to sort of wind it up, what I'm hoping it's done is shown how profound the effects of CO2 are. A simple waste product from metabolism is being used by the body to govern and control many, many, many processes. You could almost argue nearly all the processes that are in the body are somehow influenced by CO2. And if they're not influenced by it directly, they're influenced by pH changes, and they can be local and regional. And it's just it is really very, very clever. Things in the lungs like hypoxic, vasoconstriction, again related to CO2 levels. I do think it's fascinating. So I'm hoping that the podcast has expanded that thought about CO2, how important it is, and how, therefore, when we got patients anesthetized, it's so important to keep that end total CO2 at 40, which gives your pH at 7.4. Those two are very, very closely related. You can't change one without changing the other. So hopefully people will think Okay, now I understand why end-tidal CO2 is so important, because it
Yeah.
has such a massive effect on your body. And the oxygen, I know we talked quite a lot about oxygen, but it's such a smaller part of what's going on. It's just the fuel, and the fuel is delivered. But once you get that fuel and start burning it or helping it to burn sugars and fats, then what happens afterwards is so clever. You think, you could have just had a body get rid of CO2, but what it's done is taking it and it's actually used it to its full advantage to control oxygen delivery, to control all these other conditions. It's just fascinating. Anyway, I've talked lots, and I think probably it's the end of our podcast today. But we'll come back. We've got another one to do on carbon dioxide. We'd look at some of the more the physiology and perhaps glide then into some of the more practical aspects of capnography in that podcast, and perhaps a later one after that. Any winding thoughts or winding up thoughts, Courtney, on
No, I just think it's amazing that we've managed to talk for close to, if not an hour, on just CO2, how it's formed, and then we haven't even breathed it out yet.
No,
we haven't got to that yet, and how these changes are all over the body. And I think up until very recently, I just thought, oh, my capnograph just gives me this number. I got to make sure it's normal, tells me if the patient's breathing all right. And it's so much more than that. It's this not a bad guy. It's this really good guy in control of so many things in the body. So I find it quite fascinating. So I'm really looking forward as well how we can start, what happens when we go to breathe it out, and then how we monitor and manage that in the next episode.
Yeah, I think it's like an iceberg, really, isn't it? What you see in it with end-tidal CO2 capnography is the tip of an iceberg. You just see the end result of, I guess, what is millions and millions of years of evolution to arrive at that point.
Yeah.
Okay, very good. I look forward to the next one, which will be in a couple of weeks.
Yeah.
Thanks everybody for listening, and nice to talk to you, Courtney.
See you later, everyone.
We'll speak soon. Bye now.
Bye-bye.
Thanks for listening to this week's podcast. Don't forget to follow our podcast to stay up to date with the latest episodes. And feel free to share this with your team. If you have any questions or feedback for us, or simply want to know more about what you've just heard, please feel free to send us an email at clinicalsupport@burtons.uk.com. Thanks for listening, and catch you next time.